On the face of it, the problem of making nitrogen should be a simple one. All one's got to do is to make the nitrogen and the oxygen in the air combine. But we already know that nitrogen is a very unreactive element and requires truly a prodigious amount of energy to make it combine with the oxygen. Not unexpectedly, nature has found their own way of doing it. Lightning makes some of the nitrogen and oxygen in the air combine to make oxides of nitrogen, which dissolve in rainwater to make nitric and nitrous acid, the parent substances of all nitrates. At the turn of the century, the nearest man-made thing to lightning was the electric arc. The arc does make some oxides of nitrogen, but an enormous amount of electricity is needed, and only 3% of it is converted into chemical energy. Only countries with huge supplies of hydroelectric power could hope to use this method. One of these was Norway, where the Birkeland-Ide process used rows of electric furnaces to make oxides of nitrogen. It was successful for a time, but for every other country in Europe, it was impossibly expensive. Combining nitrogen with oxygen didn't work, and chemists had to find another method. The white tornado strikes again. And what's the magic ingredient? It's ammonia. Ammonia is used in many cleaning products because it attacks grease and helps to dissolve it. In its pure form, ammonia isn't a solution like this, but a gas made by combining hydrogen with nitrogen. Structurally, it's really rather like nitrate. You remember in nitrate, we have a center nitrogen atom surrounded by 3 oxygen atoms. In ammonia, we have the same center nitrogen atom, but this time surrounded by 3 hydrogen atoms. The problem of making ammonia is, as ever, the inertness of nitrogen. Mix the two gases and nothing happens. Pass an electric arc through them and not enough ammonia is produced. The man who finally solved the problem of making ammonia lived at the turn of the century. He was a Prussian. In fact, he was almost a comic strip Prussian. Rigid and disciplinarian, with a highly developed sense of patriotism, Fritz Haber looked just like the stereotype of a German professor. Nonetheless, he was a gifted teacher and a talented researcher. And in approaching the ammonia problem, he used the traditional weapons of the physical chemist: pressure, temperature, and a catalyst. The molecules in a gas mixture are widely spaced apart, and it's difficult for them to react together. In a sense, they're like people in the rush hour, all busily in motion, but not making much contact. But push those people closer together in a party, and interaction starts to take place. That's what pressure does to molecules. It reduces their room for maneuver. Music is analogous to temperature. Heat gets the molecules moving faster, and the number of interactions is increased. But for really intimate contact, you need somewhere you can settle. And at a molecular level, this function is performed by a catalyst, a surface where molecules can combine to make new compounds. What Fritz Haber did was to define the temperature and pressure conditions for making ammonia and to find a catalyst, osmium, on which nitrogen and hydrogen could combine. This is a replica of Haber's laboratory apparatus. It was actually made in Haber's workshop and is now in the Deutsche Museum in Munich. It consists of 3 parts. The most important part is a reaction vessel in which hydrogen and nitrogen at a temperature of 600 degrees centigrade and at a pressure of 200 atmospheres in the presence of a catalyst are persuaded in part to combine into ammonia and are then pumped away into a refrigeration unit. The ammonia which has been produced is condensed and can be drawn off as a liquid at the bottom here. The gases which haven't reacted are dried in this regenerator and returned to the process. The real breakthrough was that up to 8% of the feedstock gases could be converted into ammonia. And this made the process economically viable.